of triangles, we have 4 different centers of triangles. They are created by different parts of the triangle, and they all have different attributes, I guess you would say. So there's a little acronym. The first part of it is all of my children, and then the next part is our bringing in peanut butter cookies. So let's see what this stands for, okay? All of stands for the altitudes create the orthocenter. Okay, all of says that the altitudes create the orthocenter. So let's look at this picture there. On your picture, I already have the altitudes drawn in because they're a little tricky to draw in there. First of all, we need to know what an altitude is, if you didn't already know. An altitude is created by a vertex connected to the opposite side so that it is perpendicular to that side. So what has been done in your model there is I have connected vertex A to the opposite side so that a right angle is created at the point where it touches that opposite side, okay? I've connected vertex B to the opposite side, AC, so that a right angle is created right there. And then vertex C as well, I've connected to the other side so there's a right angle. Notice these 3 altitudes intersect at one point right there, and that point is the orthocenter. That point is what we call the orthocenter. Depending on what kind of triangle you're looking at, sometimes these centers are not actually inside the triangle. Okay, sometimes the centers are not actually inside the triangle. It is possible for the orthocenter to be on the triangle. For example, in the case of, I think, a right triangle, the orthocenter would actually be on one of the vertex. And it is possible for it to be outside of the triangle as well. Now, the thing about the orthocenter is it doesn't really have any special properties other than the fact that it is created by the intersection of all the altitudes. Okay, so the important thing here to know is that the altitudes, the intersection of the altitudes creates the orthocenter. So that one's more just a vocabulary. Now, the next part of the acronym is says my children. Okay, my children. M stands for the medians. M stands for the medians, and children stands for the centroid. Okay, medians stands for centroid. All right, so a median is the middle of each side of the triangle. So there on your triangles, I've already marked the middle point, the midpoint of each side. So what I need you to do is I need you to either take the ruler that's in the pencil box or some form of straight edge, and I want you to extend these little marks that I've made. Okay, you could use the side of your other sheet of paper, whatever, the side of your calculator, anything that's a straight edge. Okay, use it to extend these lines. Okay, so you should extend your lines kind of like I've done up here. Okay, so just draw a straight line through that midpoint right there. And they should all three intersect in about the same vicinity as what I've got up here on this picture. Okay. That point right there is the centroid. Okay, that point right there is what we call the centroid. Notice all these triangles that I'm using here, they're the same triangle. Okay, they are the same triangle. So notice that the orthocenter is in a different location than the centroid is. Okay, the orthocenter is in a different location than the centroid is. And depending on the way that your triangle is lined up, your centroid will be in different places. All right, so here is the distance from a vertex to the centroid is, oh wait, my bad. I'm so sorry. I drew my medians wrong. I'm sorry. You got to connect the midpoint to the vertex. I'm sorry. Connect the midpoint to the vertex. That was my fault. Sorry. Even the teacher makes mistakes. Okay. Fix it. From the midpoint that I have marked, draw your line through the opposite vertex. Okay, the midpoint that I have marked, draw the line to the opposite vertex. I caught something looking right there. There's the centroid. Still in a different place, bless you. Still in a different place, just not quite as close to that side AC. Mistake. Well, that's why there are rulers and okay, here's the property. The distance from a vertex to the centroid is twice the distance from the centroid to the side of the triangle. Now, those of you that are currently holding the ruler, you could measure this out, okay? Measure the distance from the vertex to the centroid. So I'm going to start with the segment here at A. Measure that distance, and then measure your distance from the centroid to the side, and it should be 2 times as long. Okay, so for example, I don't know that this is accurate, but let's say that this is 5 centimeters, then from the vertex to the centroid should be 10 centimeters. Okay, so if the distance from the centroid to the side is 5, then the distance from the centroid to the vertex should be 10. If they give you the length of the whole thing, okay, if they give you the length of the whole thing, so say, for example, I'm just going to put another point over here, and I'm going to say that this is X. If I say that BX is equal to 24, okay, if I say that BX, that segment from vertex B to that point X on the opposite side is 24, and since that's the centroid, we're going to call that middle point C. If I want to know what's the length of BC, okay, I know that the whole length is 24, and one piece is twice as long as the other piece. So let's say the other piece is Y, then this piece is 2Y. So together, how long is the segment? 3Y. So 8 is equal to Y, so this piece is 8, and this piece would be 16, so BC would be equal to 16. Okay, it's all based off the relationship that the distance from the vertex to the centroid is twice as long as the distance from the centroid to the side of the triangle. And in the pictures, that should look pretty obvious. Okay, it should look pretty, I mean, you can't always trust the picture. They're not always drawn to scale. But if you just look at that model, you can tell that that one segment from the vertex to the centroid is definitely longer than the distance from the centroid to the side. Okay? Questions about the orthocenter or the centroid?
So is the centroid always on the bottom?
You mean on the side?
Yeah.
You mean on the bottom side of the triangle?
Yeah.
It all depends on your triangle, how it's oriented and where it's at. Okay? All right, so flip your paper over. The next part of the acronym are bringing in peanut butter cookies. Okay? Are bringing in peanut butter cookies. So are bringing is the angle bisectors. Angle bisectors is our bringing, and those create the in-center. Those create the in-center. So ABI, angle bisectors, in-center. So I have started the angle bisectors there. Okay, I have cut those angles roughly in half. Maybe off just a smidge on B, doesn't look exactly right to me, but pretty close. Okay, I've cut those angles in half for you, so do the same thing, extend those segments that I've got there. They don't have to go all the way out of the triangle, or they shouldn't have to. Okay, just draw them far enough so that they all intersect. That's your in-center. That's your in-center. Okay, so angle bisectors in-center are bringing in angle bisectors in-center. Here's your property about your in-center. Your in-center is equidistant from each side of the triangle. The in-center is equidistant from each side of the triangle, and the way that I remember that is side has an I in it. Okay, side has an I in it. So in-center starts with an I, side has an I in it. That's how I remember which one goes with which. So here's how you measure distance. Distance should always be perpendicular. So if I draw, just kind of estimate it, okay, from the in-center, draw a little segment to each side. And my picture is definitely not to scale, or I'm not good at drawing perpendicular lines, one of the two. Okay. Those distances, those segments that I have there in green should all have the same length. So I'm going to label them with X. X, X, and X. I know they don't look like it. They're a little off there. That one on the left is a little bit shorter. Okay, but I didn't really actually measure the angles, so I don't know that I have the bisectors in exactly the right spot. Yours should look a little bit better than mine, because I did measure it on your paper. Okay, those distances are all the same. The distance from the in-center to each side is equidistant. Okay, equidistant means same distance. Okay, equidistance means equal distance. Equal distance. Lots of vocabulary today. Equidistant means equal distance. Just in one word there. Okay, so angle bisectors in center. R bringing in, angle bisectors in center equidistant from the sides. All right, last one, the last part of our acronym here, peanut butter perpendicular bisectors. Perpendicular bisectors. Those create our circumcenter. Okay, peanut butter cookies, perpendicular bisectors create the circumcenter. So, for the perpendicular bisectors, okay, put the two words together. If you bisect something, what does that mean? You cut it in half. So those are the points that I have on your paper. I have the midpoints marked again on each side. Perpendicular means right angle. So, the easiest way is if you have the ruler or take a sheet of paper, okay, and put like the corner of it, line up this side of the paper with the side of the triangle, and put the edge of the paper on the midpoint, and you can draw your little perpendicular line there, okay? Line up the edge of a piece of paper or the end of the ruler with the edge of the triangle, and put the side of the paper right there at that midpoint mark, and you can draw your line. Okay, line up the side of the paper with the side of the triangle, line it up against the little mark, okay, and then draw your line. That's the best way to do it without actually like constructing it. Okay, so your circumcenter on this triangle, if my pictures are accurate here, should be a little bit closer to the bottom. So that's the circumcenter. Okay, the circumcenter is supposed to be equidistant from each, anybody got a guess? Vertex. Okay, it is equidistant from each vertex of the triangle. So if we measure the distance from the circumcenter to the vertex, okay, go straight to the vertex, straight to the other vertex, straight to the other vertex. Those distances should all be the same. It looks pretty good on my picture, except my lines are not very straight. Okay, so those distances are all the same. So in-center sides both have an I, circumcenter, they're both consonants. I don't know that that really helps. The in-center and side, they both have an I. I think that helps a little bit more. Vertex, circumcenter. All right. So those are all the properties, okay? I purposefully did not staple these papers together so that you can flip this over however many times you need to, so you can see, so you can use them, okay? Let's look at the second paper, because this is how we're going to use, this is how they're going to expect you to use this information. All right, so the first problem here says if S is the in-center of triangle JKL, what type of segment is SL? Okay, well, what did the in-center come from? R bringing in. Angle bisectors go with the in-center. So these are all angle bisectors. Okay, SL is an angle bisector. SK is an angle bisector. SJ is an angle bisector. Okay, so I mean, it may just be a question as simple as that. They're just expecting you to know that if that's an in-center, then looking at this picture, those are all angle bisectors, because angle bisectors, the intersection of the angle bisectors creates your in-center. It could be as simple as that. Now, the next one is going to require us to do a little bit of math. Okay, if R is the centroid of triangle VWX, and WR is 18, so anytime I get measurements, I immediately put them on my picture. WR is 18, find RU. Well, what's the property with the centroid? It's twice the distance. Okay, so if WR is 18, what's RU? 9. WR is 18, so RU has got to be 9. Okay? All right, another one. If P is the circumcenter of triangle ABC, find BC. Find BC. So if P is the circumcenter, let's look at our circumcenter. Circumcenter was created by perpendicular bisectors. Okay, perpendicular bisectors. So if I've got to find BC, I'm finding this entire side of the triangle. A bisector cuts something in half. Well, we're not talking about angle bisectors here. Perpendicular bisectors cut that side in half. So if BE is 14, then EC is 14. So BC is 28. Okay, BC is 28. Now, let me point out something about this one. This is not what this question asked, but because these are perpendicular bisectors, there is a right angle right there. So the question may involve the Pythagorean theorem, depending on what information they give you. Okay, it may involve the Pythagorean theorem, depending on what question they give you, because that does create a right angle. Okay, the in-center may also involve the Pythagorean theorem, because those distances to the side, when you measure that distance, it does create a right angle. All right. Okay, if V is the in-center, speaking of in-center, of triangle NPQ, find TQ. All right, so let's see here. In-center is created by angle bisectors. It's not asking me anything about the angles, though. So let's see here. The in-center is equidistant from each side. So that may come into play. First of all, I'm going to highlight which piece they're asking me for. Okay, they're asking me for TQ right here. I know that's a right angle because that distance is always measured perpendicular. They give me, hopefully you can see that there is a right triangle right here. Okay, hopefully you can see that there's a right triangle. We're looking for leg TQ. We're looking for one of the legs. They give us the hypotenuse. It's 38. We need 2 out of the 3 to be able to find the third one. Well, what do you think this 24 is sitting over here doing? We need to use that 24. Okay? If the in-center is equidistant from each side, that 24 is the distance from the in-center to that side, so it's the same distance from the center to this side. Okay, and we don't need it, but just to drive that thought home, VS is also 24. So let's set up our Pythagorean theorem. We've got 24 squared plus, this is what we're looking for. You could use TQ if you wanted to. I'm just going to use x squared is equal to 38 squared. I am going to rely on my calculator to get this answer. 24 squared, 38 squared. So we've got 576 plus x squared equal to 1444. Subtract. 868 square root 29.462. Okay, make sure it makes sense. It's the other leg, so it's got to be less than the hypotenuse, and clearly, according to the picture, it's got to be longer than the other leg. Now, according to the picture, it looks a lot longer than the other leg, but you can't always trust the picture. You're not drawn to scale. Well, the picture's drawn to scale. The sides are not labeled very well. All right, questions? Okay. All right, let's look at another one. If H is the circumcenter of triangle BCD, what type of segment is FH? So circumcenter is created by, what's the circumcenter created by? Perpendicular bisectors. So FH, look at it on the picture. What is it? A perpendicular bisector. Don't take your butt out. All right, last one. If A is the incenter of triangle CDE, find the measure of angle DEA. Okay, DEA. So, incenter, what's it created by? R bringing in angle bisectors. Okay, so these angles are cut in half. So we've got 44 labeled on that little angle there at D. So the whole angle at D is what? 88. Angle bisectors, bisector cuts something in half, so this whole thing is 88. We've got 27 down there on the little part of angle C. So what's the whole angle C? 54. They're asking us for angle DEA. DEA is half of angle E. So we've got angle D is 88, angle C is 54. What do we need to do to find angle E? Add them up and subtract from 180. Okay, to find that third angle of the triangle. 180 minus 88 minus 54. So angle E is 38, but were they asking us for angle E? No, they were asking us for the little part, which is only half. So 19 degrees is the measure of angle DEA.